When an autonomous vehicle loses its ability to stay centered in a lane, the result isn't a simple drift. The car rapidly overcorrects, oscillating wildly from side to side until it completely leaves the road. This block diagram shows the logic driving that motion through a closed-loop system. At the center is controller gain K, determining how aggressively the steering reacts. Extracting the transfer function's denominator gives the closed-loop characteristic equation, where K is the steering correction sensitivity. This is the complex S-plane, mapping the roots, or poles, of that characteristic equation. For the vehicle to drive smoothly and safely, every single pole must sit strictly on the left half side of the vertical axis. If even one of those poles crosses that vertical line into the right half plane, the physical system goes unstable. That is exactly when the car starts aggressively swerving. To guarantee safety, engineers need to know if any poles exist on the right side. But calculating the exact roots of a high-order polynomial analytically is computationally heavy, and it becomes impossible when you have an undefined variable like k sitting in the equation. We need a way to check for stability without actually solving for the roots. That workaround is the Routh-Hurwitz Criterion. It is a systematic algebraic algorithm designed specifically to count the number of unstable poles in a system. Instead of attempting to factor the polynomial, this method simply takes the existing coefficients and manipulates them. By arranging them into a matrix and running a recursive calculation, we can determine the system's stability. In classical control theory, we usually get this polynomial by extracting the denominator of a closed-loop transfer function and setting it to 0. But it applies equally well to modern systems modeled in state space representation. You arrive at the exact same characteristic equation by taking the determinant of the system matrix A subtracted from Si and setting that equal to 0. Whether you are working with transfer functions or state space matrices, Routh-Hurwitz gives you a universal algebraic tool to define operational safety limits before a physical prototype is ever built or tested. Let's see how the matrix is actually built using a standard fourth-degree characteristic equation. Our test case will be s to the fourth plus 2s cubed plus 3s squared plus 4s plus 5 equals 0. Before running the algorithm, we perform a preliminary check. We verify that all descending powers of s are present, meaning no terms are skipped, and we check that all coefficients share the same mathematical sign. In this case, they are all positive. Next, we construct the first two rows of the Routh table by interlacing our coefficients. The first row, matching the highest power of s, takes every alternating coefficient starting with the first, 1, 3, and 5. The second row takes the remaining even terms, 2, 4, and since there are no more numbers, a 0. To generate the rest of the table, we use a specific recursive formula. Every new element is calculated by taking the negative determinant of a 2x2 matrix formed from the two rows directly above it, and then dividing by the first element of the row immediately above it, our pivot element. For the first spot in the s-squared row, we cross-multiply 1 times 4 minus 2 times 3, which gives us -2. The negative determinant makes that a +2. Divide that by our pivot element, 2, and we get 1. We apply this exact same operation to calculate the second element in the row, and then we cascade this logic downward, generating the s to the first row and finally the s to the 0 row until the table is entirely populated. Now we apply the core Routh-Hurwitz rule. To detect instability, we isolate the very first column of the completed table and simply count the number of times the numerical sign changes. Moving down the column, we shift from a +1 to a -6, and then back from a -6 to a +5. Because there are exactly 2 sign changes in that first column, we know with mathematical certainty that this system has exactly 2 poles located in the right half plane. Without ever calculating the actual roots, we have proven this system is unstable. The standard algorithm works perfectly until you hit a mathematical singularity. If a 0 appears as the first element of any row, the process immediately breaks down, because the recursive formula would require dividing by 0 to find the next row. We call this case 1. To bypass the singularity, engineers simply replace that leading 0 with epsilon, representing an infinitesimally small positive number. This allows the matrix calculations to continue algebraically, using epsilon in place of the 0. Once the entire table is filled out, you evaluate stability by taking the mathematical limit of the expressions in that first column as epsilon approaches 0. This reveals the final positive or negative signs needed to count the right-hand poles. The second singularity, case 2, occurs when an entire row of the table evaluates to 0. This happens when the original characteristic equation contains purely imaginary or symmetrical roots. To resolve this, we look at the row directly above the zeros and use its values to construct an auxiliary even-powered polynomial. We then calculate the derivative of that polynomial with respect to s and substitute those new derived coefficients right back into the empty 0 row, letting us finish the table. By systematically handling these two mathematical edge cases, the Routh-Hurwitz criterion maintains continuity. It remains a robust analytical tool for dissecting any linear dynamic system. Let's bring this back to the autonomous vehicle. Our steering control system was governed by the characteristic equation s to the fourth plus 6s cubed plus 11s squared plus 6s plus k equals 0. If we run this specific polynomial through the Routh table, we don't have all the numbers, so the controller gain k acts as a variable moving through the recursive cross-multiplication steps. When we complete the process and isolate the first column, we get 1, 6, 10, and then two variable expressions, 60 minus 6k over 10, and finally k. We know that stability requires 0 sign changes in this column. Because the first three numbers are positive, we must mathematically force those last two variable expressions to also be strictly greater than 0. We set up two inequalities. K must be greater than 0, and 60 minus 6k divided by 10 must be greater than 0. Solving that second inequality tells us that k must be strictly less than 10. We now have our physical boundary. Using purely algebraic matrix manipulation, we have proven that at a gain of 10 or higher, a pole crosses into the right half plane and the car completely loses control. Finding this safe operating threshold on a relatively simple controller is just the starting point. This exact mathematical procedure scales identically to higher-order, multivariable dynamic systems. Engineers use it to lock in the stability of highly complex human-in-the-loop hardware, where closed-loop biofeedback dictates the motor control of a smart prosthetic limb. It is essential for high-precision multi-input, multi-output systems like aerodynamic drone flight, where sensor time delays must be strictly bounded so the vehicle doesn't fatally overcorrect in the air. You will find this baseline algorithm applied across completely distinct engineering disciplines, from the linear, high-precision servo controls of an MRI table to the highly coupled flexible dynamics of an industrial robotic arm. Today, control engineers rely heavily on frequency domain plotting and computational root locus design for detailed fine-tuning. But before any software models the precise transient response, the Routh-Hurwitz criterion serves as the mathematical bedrock, drawing the absolute line between a functioning machine and total systemic failure.